Simpkins Physics Corner coming to you with a work and energy related, actually this is just a straight conservation of energy problem for academic physics. Let's jump right into it. A stone with a mass of 5 kilograms sits on the edge of a cliff 25 meters high. So we got a 25-meter high cliff, and the stone has a mass of 5 kilograms. What is the gravitational potential energy of the rock at the top of the cliff? All right, so what do we know? We know that the mass is 5 kilograms, and we know that the y, or the height, y, how high, got it. Like in math class, the y-axis is vertical. The y, or the height of the cliff, is 25 meters. So it says, what's the GPE of the rock at the top of the cliff? GPE, just short for gravitational potential energy. Well, we learned in our crash course physics video that the gravitational potential energy, or GPE, is equal to mgy. mgy. So if I want to calculate the gravitational potential energy, all I have to do is look at my list of knowns that I made and go ahead and plug everything in. So the mass is 5 kilograms. The g, the gravitational acceleration near the surface of the Earth, is 9.8 meters per second squared. And the y is 25 meters. So if I go ahead and drop that into my calculadora, that'd be 125 times 9.8. Just multiply everything together. And it looks like my initial potential energy at the top of the cliff is 1,225 joules. Okay, so the question number 2 says the stone falls from the cliff. What is the kinetic energy just before hitting the ground? Now, the video you should have just watched was the work and energy and conservation lesson. And in that lesson, we covered that the total energy of a system has to remain the same if it's a closed system, which in this case we do have. The potential energy started as 1,225 joules. Well, if that's how much energy we had all the way at the top, let me shift colors for you to make things interesting. If I look at how much energy we had all the way at the top, let's go for, I don't know, blue. The total potential energy at the top was 1,225. 1,225 joules. And apparently it didn't change colors, so that's fantastic. But that is the total energy, and we weren't moving, so we had 0 kinetic energy. So what's 0 plus 1,225? 1,225. And what does that mean? Well, this says the stone falls, what's the kinetic energy just before hitting the ground? Okay, if I'm about to hit the ground, what's my height? My height is 0. And if my height is 0, or really I should say my y is 0, right? Y is how high, your height. If my y is 0, then what's my potential energy? Oh, 0. I don't have the potential to fall anymore if I'm about to hit the ground, right? I'm almost there. So that means that we have 0 GPE. Well, what does that mean then? Where did that energy go? Well, the force of friction did work on the stone as it fell, and when work is done, energy changes. I hope you're saying it by now. When work is done, energy changes. It doesn't change amount, it changes form. And we started with 1,225 joules of potential energy, so what does that mean? That means that that energy has been converted into a different form. Because we are at a height of 0 effectively, all the energy is kinetic at that point. Why? Because all the energy has to add up to the same total, 1,225. Okay, so that's number 2. The number 2 is asserting that because of the law of conservation of energy, the potential energy was converted to kinetic energy because there's no longer a height right before you hit the ground. Draw a sketch of the stone box to the left, labeling the GPE and KE at the top and bottom. All right, so down here, the KE is 1225. And the GPE is 0, again, because we're just about to hit the ground, so we pretty much don't have any GPE. Here's an interesting one. How fast is the rock moving just before it hits the ground? How fast? Well, how fast is motion, and motion is associated with kinetic energy, so I wonder if there's some way to relate kinetic energy to velocity. Oh, well, if we consider the physics crash course lesson we watched and the notes that we took, kinetic energy is 1/2 mv squared. So let's go ahead and plug in what we know here. We know that the kinetic energy right before we hit the ground is 1225 joules. We have the 1/2, and we can see that the mass of the stone is 5 kilograms from reading the initial problem. And so all we have to do here is solve for v squared. So you'd have to divide both sides by 2.5, because that's half of 5. 1/2 of 5 is 2.5. And so if I take 1225 divided by 2.5, that's going to get me 490. Now, you have to be careful. We didn't just solve for velocity yet. We just solved for v squared. How fast is it moving? We're asked to solve for velocity. So the final step is to take the square root of both sides. Now, if I take the square root of 490, I get 22.13. So v equals 22.13. And so we, Yes, I want to keep my annotations. And so we see here that with the law of conservation of energy, we can keep track of it. We can say, well, at the top it was all potential, at the bottom it's all kinetic. Now, if you're anywhere in between, things get a little trickier, and we're going to go over that in our next lesson tomorrow, or sorry, on Thursday. But for now, what I want you guys to do is take a look at the handout. The next problem is just like this one. So if you're not sure what to do, come back, rewatch this video, pause it if you need to, and go through these ideas. Once you're done with filling in your notes and doing that last problem, you can go ahead and drop it onto Canvas on the assignment. Until next time, it's Mr. Simpkins in the Simpkins Physics Corner.